Low-latency FPGA-based electronic control system for fast preparation of defect-free atom arrays.
You won't believe what these researchers did. They built an ultra-fast FPGA-based control system that can prepare perfect atom arrays in record time.
Really? I thought preparing quantum systems was always slow and clunky.
Exactly the opposite. They cut feedback latency down to under 300 microseconds, which is fast enough to actually correct errors while the atoms are still dancing around.
Wait, how do they even see what's happening?
They integrated photon counting right into the control chip, so they know instantly when an atom lands in a trap.
That sounds like something out of a sci-fi movie.
It is. And it means we're getting closer to running useful quantum programs without them falling apart.
Okay, but why does latency matter so much?
Because every millisecond counts when you're trying to keep qubits stable. Even tiny delays can ruin an entire operation.
So what did they actually build?
An FPGA platform that handles photon detection, decision-making, and waveform generation all at once. No PC bottleneck allowed.
That sounds pretty clever.
It is, and it lets them rearrange hundreds of atoms into a neat grid without ever losing track of where each one went.
So they can make defect-free arrays?
Absolutely. They build 24 optical tweezers that load atoms stochastically and then reorganize them with over 95% success in just a few steps.
Wow, so this system basically makes quantum experiments faster and more reliable than ever before. All right, Jamie. Let's dive into the experimental system part. I know this is all about quantum processing with neutral atom arrays, but can you give us a quick picture of what the setup actually looks like?
Sure, Alex. Imagine we've got a one-dimensional line of atoms floating in a vacuum chamber. Tiny marbles suspended by light beams. That's our atomic array.
Okay, so we have the atoms themselves first. What's next?
Those atoms need to be trapped and manipulated. There's a classical link, a system of lasers and optics that delivers the light needed to hold and move each atom around.
Got it. And then what happens?
After that, we have the quantum link catching the faint light they emit when excited, to gather information about each atom without disturbing them too much.
Nice analogy. So we're collecting data from these tiny light signals?
Exactly. Then there's a classical control module that takes all that data, decides what to do next, and sends back the instructions, like a conductor telling each musician when to play.
Sounds like a pretty high-tech orchestra. What about the actual hardware? I see terms like volcano architecture and PXIe system.
The volcano setup routes light from different channels into one place for simultaneous detection, like several microphones feeding into a single recorder. The PXIe platform ties everything together, letting us process signals super fast.
So this whole system is designed to minimize delays?
Precisely. We're talking about reducing latency from data capture all the way back to feedback commands because timing matters when you're dealing with microsecond scale operations.
And what's the big number here? Why does it matter so much?
Building on that gain we mentioned, the electronic system latency is around 282 microseconds. Compare that to older setups running on a PC, which took over 7 milliseconds. That's 10 times slower in terms of real-time feedback for atom rearrangement and error correction. This is huge.
That's incredible. So what happens when you actually use this setup?
We can rearrange atoms with much higher success rates, up to 95% in some cases. And because we're running everything in real time, we open the door for mid-circuit measurements and even early attempts at quantum error correction.
Wow, so it's not just about making qubits work, it's about doing it fast enough to actually correct mistakes as they happen.
Exactly. This system gives us a serious step toward practical fault-tolerant quantum computers using neutral atoms.
Thanks, Jamie. This really paints the picture of how all those lasers, chips, and control boards come together in action. So we've been talking about how these quantum processors work, but I'm still not clear on the actual rearrangement process.
Great question. Let me break down what happens with those atom arrays.
Okay, hit me with it then.
All right, picture this. They have a chip called an OCM, right? It's like a tiny highway for photons. Each trap on the atomic array sends out fluorescence that gets funneled into individual detectors.
Got it. So each atom's light goes its own lane to be measured.
Exactly. And what makes this cool is they detect which traps have atoms and then rearrange them without any human intervention.
Wait, no humans? How does the system know where everything is?
Well, first they cool these atoms down super precisely using laser techniques. Think of it as giving each atom a precise temperature setting.
So they're basically playing a high-stakes game of atomic Tetris?
Exactly. Once they know where everything is, the system calculates paths for atoms to move into place using radio frequency commands.
And these commands get sent through this whole chain of electronics and processors?
Right. There's a really fast FPGA chip doing most of the heavy lifting in milliseconds. The whole thing is designed so they can rearrange all 24 traps on their 5-millisecond cycle time.
That's wild. So they're not just detecting, but actively reorganizing the entire array mid-experiment.
Precisely. And after rearrangement, they check if there are any defects, like an empty trap where it should have an atom.
How do they know which traps became defective?
They compare before and after photon counts to spot missing atoms. Then they use this feedback loop to plan the next move.
I love that they're constantly optimizing their own setup without stopping.
It's like a self-driving car for atoms, constantly scanning, adjusting, and moving forward.
So if an atom gets bumped out of place during rearrangement?
The system actually detects that too through the same fluorescence monitoring and can replan paths on the fly.
That's some next-level automation right there.
And all this happens within a carefully controlled vacuum environment, where even tiny magnetic fields could mess things up.
So they're not just moving atoms around, they're maintaining an entire ecosystem of ultra-cold particles and photon channels?
Exactly. It's like orchestrating a ballet, but with lasers and quantum states instead of dances.
All right, Jamie. So I've been glued to this part about how fast the system reacts after it detects an atom. What's the big deal with that timing?
Think of it like a high-speed relay race, where each runner has to hand off the baton at just the right moment. In our setup, we're measuring how quickly the detection pulse triggers the next step, the electronic latency.
So you measured this in a trace diagram? What does that blue line represent again?
The blue line marks the detection completion pulse, the moment we know an atom has been found. Then there's a yellow square wave that pops up after, signaling that the rearrangement command is sent to the traps.
And what was that number they settled on?
In their experiment, when everything lined up just right, they found a total electronic latency of about 32 microseconds, so roughly 0.00032 seconds.
Wow, that's like catching lightning in a bottle. But why does it matter so much?
Because every microsecond counts when you're moving atoms around with precision. If the latency is too high, the atom can drift or get lost before the trap even knows to move it again.
So they actually tried different things to trim that time down?
Exactly. They experimented with keeping the detection pulse consistent and then varying how quickly the system could process and send out the trigger signal.
And did it actually improve their results?
Yes, with those lower delays, they saw higher success probabilities for arranging defect-free atom arrays, especially when they ran multiple rounds of rearrangement.
So it's not just a single measurement, it's about stacking improvements on top of each other?
Precisely. The latency isn't static. It drops further as they optimize each step, and this cumulative effect makes a huge difference in practical applications.
That's wild. So if you can shave off even a tiny bit of time per cycle, over many cycles your success rate skyrockets?
Exactly. It's the kind of behind-the-scenes engineering that lets complex quantum experiments actually work reliably in real life.
All right, Jamie. Thanks for breaking this down. I think listeners will appreciate knowing how timing is just as crucial as the atoms themselves.
Exactly. They skip sending full raw data and instead transmit only the comparison results once an atom is detected. Kind of like telling a friend you saw a cat, rather than describing every step you took to see it.
So that keeps things snappy even when dealing with 24 potential spots? I noticed the histogram showing latency spread across thousands of trials. Why does that distribution matter so much in real experiments?
The histogram tells us how consistent their system is. If each run had wildly different latencies, planning precise rearrangements would be chaotic, like coordinating a synchronized swimming routine with uneven timing.
That makes sense. And what about the three optimizations they listed? Bypassing PC communication first? Why is that such a big deal?
Most computers introduce delays when handling data over USB or PCIe protocols, much like traffic jams slow your commute. By going direct with FPGA and ARM processing, they cut out those extra stops.
Okay, so the ARM only needs to know if a detection happened or not? How does it actually figure out where the atoms are after that?
The counter card kicks in as soon as the trigger comes in. Then the CPU runs quick calculations, just 4 nanoseconds per decision, and compares results against thresholds. It's like having an instant scoreboard for a game.
And I see they're using binarized comparison values instead of full counts to save time on readout latency. But wouldn't that lose some detail?
Not necessarily. Retaining raw data helps during debugging, while the simplified mode just reduces transmission load without sacrificing accuracy when checking if rearrangement succeeded.
So altogether, they've built a system where atoms move quickly because their control loop is razor sharp.
Precisely. And that 282 microsecond total latency sets the stage for faster cycles in future experiments, though there's still room to push beyond those single-round limits.
I'm curious what happens when you try to scale this up or run more rounds. Does the timing hold steady?
That's exactly where we're headed next. The trade-offs as they attempt multiple rounds and see how latency scales under heavier loads.
That's all we have for today. Thanks for listening, everyone.
See you next time.